So this one is going to be more from the user space perspective. It seems like so far we've been in some gory implementation details. So, I'm just teasing. I just want to start by giving you guys some clue of what we do, what Flightcaster is about. So I like to solve. I'm a researcher. I like to solve problems that are a pain in the ass, essentially. And there was a couple of years where I was doing consulting work, and most of the time was honestly at Google, so it wasn't bad. You know, like my commute was Caltrain or whatever. But for about 6 months, this was my view of the world, twice a week. And it sucked, and I was delayed a lot, and so this is how I developed an intense hatred for flight delays, which is what we predict. So this is a view of what our UI looks like. So essentially, actually, before I go any further, let me just get a kind of a show of hands, like, how many people know the different abstractions that are on top of Hadoop, like Cascading, Pig, Hive, etc.? Kind of a mix? Most? Okay, cool. And how many people are familiar with functional programming in any way and have done some functional programming? Okay, cool. And how many people have a reasonable understanding of like probability theory and stuff, that kind of, in a basic sense? Okay, good. Okay, so what we have here is basically like just a discretized density estimation that we're showing, right? We have 3 discrete classes, and we're saying here's the probability that you fall in one of these classes. This is essentially our UI. These are what our input variables are that are coming into the model, and we're showing them on the display as well. So if you see, okay, I'm gonna be delayed, you can come and have a look and see what are the input features that are leading to that prediction, right? So this is what we do in essence. Next little experiment. How many people have experienced a flight delay before? All right. And how many for like a really bad flight delay, like an hour, 2 hours? All right. And how many have, like, you know, maybe been on the tarmac, even stuck on the tarmac or something? Right. And how many of you knew it coming, like an hour or 2 hours before? Yeah, I saw 2 hands there, or maybe 3. Okay. So here's why. When we first started doing this, you know, most researchers that really want to solve a learning problem will usually start with some rudimentary statistical analysis and make sure it's not too hard, because we don't like to work on those ones, right? So we found out that really 3/4 of the flight delays are announced under 30 minutes before departure, so clearly, you know, there seemed to be some opportunity there. I'm going to tell you a quick story from Thanksgiving vacation last year about, from my own experience essentially, where I was about to leave to come back from my friend's place where I went to have Thanksgiving dinner to come back to California. Sorry about that. And what happened is I went to look up my flight, and the Flightcaster said it was going to be really delayed. Not only did it say it was going to be really delayed, remember earlier I showed you, let me just backtrack a second here. Like, all these were red. It was like really, it was what my other co-founder likes to call a total shit show. He's the airline guy, so he gets to say that kind of stuff. Anyways, so it was really bad, and I called up US Airways, who was my carrier at the time, and I said, the flight's not going to happen, like, let's do something about this, right? And the person on the other end, the agent, she said, no, it's fine, just go to the airport. And I was like, no, look at the screen here, you know, here's how it's going to go down. And I told her the different things that were happening. You know, there's a ground stop program in effect in my connecting airport in Philly, and my incoming flight hasn't even left yet. It's absolutely impossible that it's going to happen. It's the last flight of the day. There's no way you can rebook me on anything. I just want you to book me for tomorrow. And she was like, no, I can't do it, you know, because we're telling you on time. You know, the airport status and estimated status was on time. And I said, no, like, yeah, I don't know what you need to do, but you need to go look at something because it's not going to happen and I need to be rebooked. So finally she went away, and like 10, 15 minutes later came back and rebooked me. And this was 4 hours before I was leaving. And I was pretty stoked. I was like, right on. It actually worked. That was cool. So that's my story. All right. So when we originally did this, who's familiar with the Y Combinator program at all? Anyone? probably have heard about it a little bit. So it's like one of these startup incubator things. It's pretty cool. We did that. And the thing about Y Combinator is you don't really have a lot of time. It's not necessarily the kind of thing that you typically would undertake a research-driven startup with, right? It's kind of a tricky thing to do in only a matter of a few months. So, like this guy here, if you want to be fast, you have to be lazy. So, being lazy, what that's about is like not trying to build all your own infrastructure, right? So, we use a lot of open source. I'm a believer, like if you're going to take it in, then you should put it back out too. So here we have what we take in, and here we have what we put out. So we use Hadoop. We use Cascading on top of Hadoop, and we'll talk more about this in a minute. We use Clojure to wrap those guys. And the projects we put out are this thing Infer, which is basically just a bunch of machine learning and statistics code for Clojure. We put out Cascading Clojure, which is our wrappers around cascading. This thing Crane, which is essentially a config and deploy tool, if you will, for Clojure. But there's some other cool stuff that it does that we'll talk about later with the motivations. So let's dive in now to what we're really doing. Take a look. You guys understand the problem kind of from a high level. So these are our main data providers. We take in data from FlightStats. FlightStats is a feed aggregator from all the air carriers. So this is our carrier data. This is where we're finding data on your inbound flight and all that kind of stuff, right? We take in data from the FAA. The FAA puts programs into effect. If you think about the total network of planes as a graph, the network of planes and airports as a graph, what really happens is that capacity into a certain node will be decreased, let's say because of weather. Let's say visibility goes below some threshold. They'll have to space the planes out more, decreases flow into that node. This is what the FAA data is all about. They put programs into effect and we use those as a predictor. The other is weather that we get from NOAA. NOAA has two sources of weather, METARs and TAFs. METARs are what's happening now. TAFs are predictions for hours in advance. So those are the main three sources. So what's this all about? Well, doing analysis with time in a large scale is actually a really hard problem, and transforming the data into the view that you need is very tricky, particularly when you're dealing with network data like this, where the whole, you could think of looking at everything that's happening at one horizontal slice in time, but it's kind of large and unwieldy, so you can't really do that. You have to transform it and see, like, what is it that you really want to do. So, coming into like the different ways that you can address this problem. So historically, the way that you always do this kind of thing is with a discrete event simulator. Everyone know what that is? No? A discrete event simulator is basically just, you have multiple streams, multiple time series streams, right? And you have like a priority queue or a heap data structure that's taking those streams in, and you have, or like a tournament tree or whatever implementation you're using, and is basically seeing what's the next event in time, right? And you emit these things, and the whole beast is stateful, right? As you can imagine, because it's always updating this tree. It's always emitting the next thing in time, and then your models are typically stateful. They're typically knowing what they've seen already, right? So this does not work. It doesn't parallelize. Clearly, I hope that you can see that you need a lock on that. You have to have a lock on that priority queue. So this is really not a good way to deal with really large amounts of data. It's not a good way to model it. So what are you going to do then? You can do a fuzzy join with a funky predicate. Chris is probably laughing at me because we had Chris and help me with this one day, and we were talking about this kind of stuff, and he's like, I don't know about this fuzzy join, man. Every time this comes up, it's the wrong way to go. So you don't want to go with any weird fuzzy joins. All you really need to do is this classic pattern that we seem to use a lot now that Chris kind of showed me the way to go with this, is you want to do a group by in the secondary sort, and when you're coming into the accumulator, you have these sorted events, right? And then you do a reduce over those events, and you can keep what you've seen already, what the last instance in time that you've seen already. And we create these things. Mark, this guy working with me, he calls them frames. Fair enough. It's basically it's a feature vector. So in machine learning, we call all the input variables a feature vector. It's just a vector of the different input variables that you can learn from in order to predict your target or your output variable. In our case, the multi-class flight delay that you saw earlier, where we have a % for each class. So this is what you do. And this is essentially, I call it simulating a discrete event simulator. Because you're simulating it, you're acting as if you had one of these discrete event simulators, but what you're emitting is these slices. So you're getting duplicate data, right? Think about it. You're duplicating the data significantly in some cases. But what you're getting now is an independent feature vector that has what you could see at one slice in time, right? That's the real key for this stuff and where there's a lot of nuances when you're dealing with time. It's easy to create a situation where you're doing analytics and you're using data from the future, which is of course going to give you bogus results, or you're using data that would have been overridden because maybe if you're doing like a join or something and you're doing a full Cartesian and trying to filter, maybe you're missing something and you're ending up with data that was already overridden by some new event, right? So the whole game here is to try to create these frames or these moments in time, these feature vectors in time that have only what you could see at that point in time. So that's the main data transformation. So what is this? Can't read it, looks terrible. This is my way of showing you, going into the next part of the talk here, why MapReduce is not the way that you want to program. MapReduce is what I would consider to be like an abstract syntax tree level of abstraction. It's not what you want to code in. So this is like the dot file of the Flightcaster master data transformation flow. It's relatively complex because we're dealing with all these different data sources and we have to do some things to each one and then we have to bring them together into this master simulator, right? You can't read any of this and you're not supposed to. It just looks really scary. So this is the motivation for trying to achieve greater and greater levels of abstraction, right? To get to the level where somebody like me who wants to think about solving a research problem is not trying to break everything down into individual map and reduce steps, but rather thinking in terms of higher level operations. So we've seen a number of different things come out. It seems like most of you are familiar with Pig and Hive and Cascading and so on. My personal take on it is that, so Pig and Hive are quasi-interesting for maybe doing SQL-like stuff, not so much for doing really complex data transformations like this. What I think you really want is you want to get to a level of abstraction where you're using a real programming language with higher level operations, right? And our real programming language of choice happens to be Clojure. It's pretty fantastic, but we'll talk about that in a minute. So what's the motivation? We want to do functional programming, essentially. MapReduce is fundamentally about functional operations. So there's no reason that we shouldn't just be able to do relatively normal functional programming and function composition. It's tricky to get there because there's a variety of pieces of plumbing that keep on getting in your way, but I think eventually we'll do that, and I think that's the way to go. Another motivation is that what is the dev cycle like? This typical way of dealing with distributed systems, which I've seen for years and I really dislike, is you run everything from the command line and go look at output or go look at log files or whatever, and it's really not a nice way of working when you're trying to do something complex. It's all fine when you're doing some relatively simple processing of log files, but when you're trying to weave together a bunch of really complex stuff, it's not nice. You really want an iterative development cycle. You want to be able to do good tests around your individual steps and all that stuff, right? And that stuff is rather unwieldy for the most part in most distributed systems, so Hadoop is not really the exception to the rule there, that's the norm. The other one is deploy. So, there's different stuff out there. Cloudera has some stuff out. There's EMR and so on. We want a simple and Lispy way of doing deployment in config. So what we do is essentially we spring up a REPL on a socket on the master node, a Clojure REPL, and that REPL can execute jobs, and we can send jobs to it by sending it Lisp expressions. So it's very, very simple. And not only that, we can launch that cluster from our REPL. So I can launch a cluster from my REPL in Emacs, and I can then deploy jobs from that same REPL in Emacs, right? So What we're ultimately trying to get to now, we're not quite there yet, but there's still more, is to have something like MATLAB or Mathematica in Emacs, where you're working in Lisp, but you're able to do your work on arbitrarily many nodes on MapReduce. So that's the whole game here, is trying to get up to this high level of abstraction and get the plumbing out of the way of someone trying to do research, right? So lessons learned. What have we learned from doing this? Because actually the first implementation of it kind of stunk, and we learned a lot from that. So one thing we learned is, well, first of all, like I said earlier, you want a planner. So the planner that's in Cascading or in Pig or Hive or whatever is really key. You don't want to be the one. It's just like writing your AST directly, which, I mean, of course, we're doing Lisp, so we're kind of doing that, but that's separate. It's a separate matter, right? It's like writing Java's AST directly, okay? It's not the same, right? So you don't really want to do that. You want a compiler or something, so that's what the planner thing is all about. You want something that maps down to actual map and reduce tasks. You want something that's going to be smart and string things together. We ultimately would like things that are really clever about figuring out combiner tricks and all that. And so the planner thing is really pretty key. The other thing we learned is, so, being Lispers, we like to just read and write expressions and use the Lisp reader. Not the way to go, pretty slow compared to serialization, so don't try that. Yeah, it's okay, but it's really not very fast compared to serialization, so that was kind of an error. Yeah. The other thing is, like, so wide data, right? So we want to build these feature vectors of raw data before we classify them into what will eventually be much, much denser vectors, because they'll have maybe 20 ints or something like that, right? Which is dense. But if you've got, let's say, like 6 pieces of data that ultimately classify into those 20 ints, those 6 pieces of data could each themselves be, let's say, associative maps with, I don't know, 20 to 50 elements in there. So you got to watch out when you have wide data. Like, so we have these problems like with Cascading where there's fields, right? You don't want to code 200 fields, so you want to be clever about how you put them into other data structures. So really, we found that this is pretty key, and we'll come back to this in a moment. Just operating on data structures as an abstraction for the future, if you will. So future direction, like I said, functions and data structures. So I think that this should really be the way, personally, for MapReduce in the future. I think we're kind of moving in this direction, but I would like to see things accelerate, where, you don't, like if you have a group, like if you have a grouping function or a join function or whatever, right? You should have data structures, and you should have these things be functions that operate on those data structures. And that way you don't have to always do these weird, which any people really working with these things a lot know, you're always extracting keys, special keys, so that you can group on that key, right? You'll extract like 10 things and gnarl them together into some string so that you can group on that. And like, we can't just have like first-class predicates and stuff, really, and that's kind of the better way to go, I think. The other one is that abstractions for the planner and MR or MapReduce should be really like clear and clean, and we should be able to build different stuff on top of them. And that's not happening yet at all, really. That's really very fragmented. So I think the best step in this direction is cascading, but I think we can get even beyond this eventually if we start to think more in terms of like what we're doing is manipulating data structures with functions, and if we think about it like that, I think we can go a long way. So this is me, my business card. Yeah. One thing I wanted you to do, I kind of forgot about this, but we'll do it now. That's some different code. Is to show you a little code. I know the font isn't very big, but the point is to show you that the code isn't very big, right? So, for example, this is a case here, this is gate matching. So one of the things that we have to do that's really nasty is, so if you want to know your inbound flight, what's going to be the plane that's servicing your flight? So you can see, because of course if that one's delayed, then you're not really in very good shape, right? So it's a pretty important input variable to look at, right? So the thing is, unfortunately, that these aren't published in real time. So you can't, the hash ID for the individual aircraft is not published in real time. So if you understand what that means you cannot group on that. You cannot know this is the life of this airplane. You have to instead group on an amalgamation of the airline, the airport, the terminal, and the gate. And you have to look at these for departure and arrival for different planes, right? You have to bring them all into one stream, and then you have to walk that stream and try to figure out what the last thing is that's coming into the gate before yours is leaving. And then you have to match, right? So it's a heuristic, it's inherently probabilistic, and it's pretty gnarly, I'm not gonna lie. So this is what's happening here, where this is this extract, right? Like I mentioned earlier, we always have to do this thing where you extract some kind of a gnarled out key, and that's what's going on here. And then, so you're extracting these guys, you're grouping on this special gate match key, secondary sorting on the event time, right? And putting it into this gate match buffer. This buffer that I was talking about is this special thing that's really doing some pretty serious stuff in the actual aggregator function of the reduce. So as it's walking down this stream, it's carrying what you could consider state, but it's doing it in a purely functional way. So another example would be in the data flow. So in the data flow here, you can see this is where we're building those frames, those final feature vectors, where again, we're filtering. So I'll just walk you through step by step, actually, it's not that bad. So we're filtering out watched airlines because right now we're not doing international flights and we're not doing like small regional carriers and so forth. So we filter out a bunch of stuff, right? You always want to wean the stream down to be as small as you can before you go into the hard stuff. Then we're making sure, so what we have here is we're getting all the scheduled flights because we're only predicting a flight before it takes off, right? And then we're getting the arrived, and what the arrived is that's the Y that you're trying to predict, right? Like if you have a bunch of X's and a Y and you're trying to predict the Y is the plane that's actually at the gate, so you know what really happened. That's how you can score what you predicted. And that's how you can learn what happens from other input variables. Then you have the matching going on, right, that I talked about. You have the gate matching, and then you have all these programs coming in and METARs. So this is weather data and the FAA programs that I mentioned. And again, what we're doing here is we're simulating a discrete event simulator. So these guys are all pulling out, like they're pulling out flight stats IDs, which is the IDs of the plane, of an individual flight. Not of a plane, I'm sorry. They're the ID of a particular flight. So you might have 20 records per flight as you get incoming data on that flight over the course of time. So these guys all are pulling out like programs and associating them with flight stats IDs. So then when you come to here, you can group on that, and then you can again do your secondary sort on the timestamp and walk it forward and produce these different frames from the simulate function. So this is kind of what's happening here. If anyone really wants to go into some more detail, like just come out, hang out with Mark and I after, and we'd be happy to go through some code with you. Ooh, okay, there we go. So that's it. Anyone has any questions? Have at it. Yes?
What were the biggest debugging challenges that you ran into when dealing with real live data?
Biggest debugging challenges. There's a lot. It really depends on what part of the process you mean, I suppose. You know, because there's classification going on and there's data transformation going on. We do those steps discretely and independently. So, but and there's also just getting the flows to work in the first place, right? So I would say that one of the nastiest ones is so we have. I can show you also like. I don't know, we'll do it later if you want to come and ask. But we have some pretty cool stuff for testing these, which is quite nice. And so that part's actually not that bad anymore, I would say. Getting everything to work and hooking it up and getting it working together is actually now okay. Because we can do things interactively from the REPL, we can test these things like a unit testy kind of way, and that stuff's pretty okay. The part I would say is really the nastiest is that the data is quite messy that we're getting, because we're not talking about data we've captured ourselves here, and we're not talking about a technologically advanced industry necessarily, right? Like, we've seen manually edit XML, for example, right? Where like somebody just cut and paste half an XML file somehow just hammered it in later on in the file, right? So just totally wacky stuff like that. And you also see just like times that are, just utterly imparsable times, right? That make no sense. Not any part of any ISO format at all, right? So you see that kind of stuff. And then you see data, where the hour slot, you do have a valid ISO time, but then the hour slot has like 32 hours in it or something, right? So what happens is you start getting stuff working and then it blows up. And then, oh shit, there's a problem, fix that. Okay, now run it again. Okay, blows up again. So like it just keeps on blowing up and eventually you realize, like that, one of the best ones ever was the one Mark discovered yesterday. And then some of our other guys found out the real root issue going on. One of the files just had a completely invalid Unicode character in it, which I've never seen anything like it. It was it was a new paradigm for me. So yeah, I think that's the biggest problem, is just the data is nasty and we haven't really gotten a good way of dealing with that yet. So I've talked to Chris about it several times. Cascading actually has some cool stuff for this. You can do asserts and filters against it. So for example, you could state some invariants about your data that should hold, and you could run that over your data prior to doing any real processing on it, and kind of get a feel for how nasty it is or what kind of issues are there. And you can, with a filter, you can save that off, right? So you can save off the data that's erroneous and then go have a look at it and see what's wrong with it and then try to make your code more tolerant to those faults. Yeah. Uh-huh. Oh, there's two of you, so I don't know. You guys are going to have to fight amongst yourselves.
Was this a Hadoop project from the beginning, or did you hit a point where you realized you needed scale and distributed systems?
No, it was from the beginning. Yeah, I knew it was going to get that messy. And to be honest, our data is not super huge.
That's my question. So like a whole lot of data, but
it's actually, so this is an interesting thing where I would argue that this stuff is not only about data that's big, but also complex data operations. Like what we do, I would never want to try to express in like SQL. It's not a relational set thing, It would be pretty funky, I think. So, I think that you get a lot from these kind of things like cascading, in terms of just getting you up into a level of abstraction for doing really complex data transformation. So, although our data is not, Yahoo scale or something like that, it's big enough so that it's probably not a good thing to attempt on one big giant monolithic machine or something. But yeah, we started it from the beginning like this. So. Mm-hmm.
So this hub that you wrote, what is it?
Oh yeah, so we have a couple of open source projects. We just moved it to this thing on GitHub called CLJ-sys, which is kind of like, the idea is to try to have a nice central location for a bunch of Clojure systems level programming stuff. CLJ-sys on GitHub, yeah? It's CLJ-sys. And we have the crane thing is over there, which is pretty neat. That's interesting and worth looking at. And then the cascading Clojure stuff is on there. And the new, we kind of rewrote and gutted most of it, and the new wrapper is actually pretty nice to use as well. So yeah, come check them both out, definitely. Mm-hmm.
I've seen the Scala guys also doing a functional approach.
Mm-hmm.
To do, one of the approaches was to take closures and turn those into schedules that you can stick on a mapper right away.
Mm-hmm.
And I was wondering if you could contrast your approach using cascading
mm-hmm.
versus taking a form and directly translating it to something you can put on a mapper.
Well,
would that work here?
No, I mean the idea is more or less the same. The thing is that, with cascading, we're not operating at the raw MapReduce, right? We're instead wrapping things like group by, right, and things like filter. And so, rather, the idea is the same, of course, that like these things are just functions. And so you just want to be able to serialize a function and give it, and that's it. But we're wrapping, I would say, a higher level interface, which is one thing. The other thing is, we can't really serialize anonymous functions yet, as it is now. We kind of can, but there's nuances to that. So we define functions, but not necessarily anonymously yet. Yeah.
As far as concurrency goes,
mm-hmm.
are you cascading? You're based on a pipeline there, or are you getting some verification on the cascading there?
Not exactly sure of the question.
Data operation serializing?
Data operation serializing. Yeah, I mean, it's just like normal MapReduce, right? So there's no special, we're not using any Clojure has really cool concurrency primitives, for example, we're not using any of that. It's just the normal MapReduce, everything's being serialized as normal, yeah, right? So what we're doing is, for example, if we return a Clojure data structure, then we're serializing those, you know? So we put things back and forth into JSON and so on. So it's all vanilla stuff as far as that goes. There's nothing really super magic that we do.
Your filter operation, are those running in parallel?
Yeah, yeah. Mm-hmm.
So do you actually, I'm just curious, do you happen to do any of the parallelization at the Clojure level itself?
Mm.
It's kind of nice language to do.
Right, right.
Basically, my question is, if you have a really beefy node,
Mm-hmm.
within the language itself,
Right.
that must be an opportunity to go parallel.
Yeah. No, it's a great question and something that I've definitely been thinking about and wondering, if we would consider. The question was, do we use Clojure's parallelism? And we don't really as of yet, but I think there's definitely some cool stuff that you could consider with that because it is quite nice, And I guess if you're doing let's say if you need to do something, for example, within a mapper or within a reducer, which itself is calling, let's say a map, then you would probably want to try to use Clojure's parallel map, for example. Yeah, so there's definitely some stuff that we want to explore with this. This is all rather new, so in terms of a lot of performance optimization, we haven't done a ton yet. We've just really scratched the surface as far as that goes. Try to make sure. Actually, just yesterday, Mark was kind of ironing out just like our top level, really egregious things, but we haven't gotten into any of the really neat stuff that you might think about there. Yeah. Mm-hmm.
So where is your discrete event simulator? Is this a separate module that you're calling from here? Or where is the time wheel, or where do you insert the events and so on?
It's just, yeah, we can show that. So let's see. The simulator is really, this is it here. So this is all it is. I mean, it's just a function, right? Like everything. That's the nice thing.
Where is the integration with Hadoop then? I mean, where do you call MapReduce?
Oh, so Cascading has what's called aggregators, which is what's happening in the reduce side, right? And in a cascading buffer, you can get a hold to the iterator for what's coming into the reduce. And so we get a hold to that iterator, and then we just walk the iterator. And each new event we see, you can see up here, we're just like walking and seeing what kind of event is it, and then we decide what kind of a frame to emit based upon what we're seeing now and what the last things we saw are of different kinds. So that's it. It's just happening in a reduce. That's the cool part of this, is like we're doing away with the model of a discrete event simulator, and kind of we're mimicking that inside of a reduce with an aggregator that's a little bit funky, because what it's carrying forward is carrying a state of the last things that it's seen.
So you're doing a map and a reduce?
A map and a reduce. No, I mean, there's many stages to it, but these little simulator guys, which happen actually in several places, because there's several places where you need to do this. These do happen in, essentially inside of a reduce, right? Yep.
So how many events typically do you have in a simulation?
Let's see, I mean, I'm not sure from the recent one. It's going to be hundreds of millions, in the order of hundreds of millions. So not into the billions, but reasonably large.
At what rate?
At what rate? What do you mean?
You say hundreds of millions of events per, that's total.
Oh, yeah, total, right. Yeah, so in total we'll have hundreds of millions of frames that we're looking at. Yeah, because, I mean, we've seen, there's way more events than that we have, but many of them are filtered out because either the airport, or I'm sorry, it's not an airline that we watch, or it's an international flight, or it doesn't have adequate data for us to look at, so we filter a number of things out.
These map producers, what is the window that their state operates within?
I mean, at the very end, it's just a simulator for one flight. So over the life of a flight.
they save some state, right? But I'm curious what the window of that state is.
Oh, it's only the most recent thing it's seen of each event type, right? So if we have if we have a flight, and then we have data for its inbound flight, and then we have like FAA data and then weather data, it's only a one frame look back, right? So it's not a rolling window situation. Well, it is, but it's a rolling window of one. Yeah, exactly. So it's not like it gets really, really gnarly there. But the thing is, though, so one thing that we probably want to change, and Chris is probably going to be pissed off when I admit this, but we're building up all of the frames inside the reducer as well as a giant vector, and then we emit them at the end, when really what we should be doing is probably passing in the iterator and appending them to that as we go. So that probably gets pretty large. I mean, you can run into issues. We just had to like jack up the memory on the mappers and reducers because of this stuff.
How accurate is this, your prediction?
So it depends how you ask, or like what you mean by that, right? Because so if you guys know what precision and recall are, have you heard of that or no? So there's like there's given there was a delay, how often was I able to predict it? And then there's of all the delays, how many of them could I predict, right? So the latter is recall, the former is precision. So precision-wise, I think as of now we're like 60, 70-ish. And then the recall-wise, it depends on what time before departure. It's one of the nasty parts about this problem actually is the loss function is not just the normal two-dimensional loss where it's just, you know, looking at what happened and like which class the actual situation fell into and which one did you predict. It actually has a time dimension as well. So now, what's your precision and recall at 1 hour before departure, 2 hours before departure, 3 hours, and so on. And it keeps getting worse, right? So out at 4 hours before departure, we're only able to recall about 15% of the delayed flights, which is something we're working a lot on right now. As we get closer, of course, we're better. We're always better than the airline, but we want to get much, much, much better is the thing, right? We want to get way better.
How does the seasonality affect you?
The what?
The seasonality, like holidays, travel?
Yeah, sure. So, I mean, it's a great question, and there is definitely seasonal biases. There's time of day biases. Contrary to what you might think, there's not very strong day of week biases. But the big thing here, you got to remember always, is yes, there's issues in the seasonality, but the bigger issue is time of day, and the time of day is really a symptom of what the bigger problem is, because the time of day just looks worse, right? So if I showed you a curve, and it's coming this way, right, where time toward departure is coming here, or like time of day is going this way, right? It just, your delay is going to go up and up and up, and the reason is just this propagation effect, because it propagates through the network, right? But because we're a real-time service and we're looking at real-time data, we don't even look at any of those factors. We throw it all out, because it's all symptomatic of the real stuff that you want to see, which is what's happening with these delays, you know, as they're propagating through time. So what's happening with my plane that's going to come to pick me up, and what's happening with these other airports that are going to decide to let me take off or not let me take off because of different conditions going on there. So we actually throw all that out for the real-time model. Now, we would look at that when we start to do predictions at greater than 24 hours before departure, which is something we'd like to do soon. And in that case, then you really want that kind of data, because you don't have any of that cool real-time stuff going on. All you have is like one observation per flight, and you have no information on what the estimated times are or anything else. You have no idea what's going on throughout the network at all. So in that case, you definitely do want to know what time of year is it, what time of day is this flight supposed to be leaving, and so on. So, anything else? Yes?
Through all this data you have in analysis, can you just give a general recommendation of which airplane company is the best by far?
Right. A lot of people ask that one too. And it's actually totally contrary to what you would think. It's really not that big of an issue, interestingly enough. It's not a very informative variable. It's much more complex than that, which was surprising to me. I was expecting to see that some of them would really suck. But the thing is, though, if you talk to anyone, they'll always tell you that a different airline sucks. So it turns out that they all do, right? So it's not that informative of a variable. So yeah, it depends a lot on the airports you're going between and time of day and all this other crazy stuff. You know, it's a very complex system. So I wouldn't say I like to fly Virgin myself because they're pretty nice. You know, and I like the little purple lights in there and stuff and the lounge music. So I fly with them. You know. Anyone else? No. All right, that's it. I think Dukil's kind of turning the lights off on us. It's like kind of like staying at a restaurant too late, you know. He's stacking the chairs up and stuff.
So we're still open. Yeah, hang out, more questions. So nobody's kicking you out. Thank you very much for joining. And again, remember the Hadoop Summit on June 29th, and we'll see you all next month at April 21st. Thank you for your time. Drive safely after all the beers.